Okay, so what we're going to go over today, guys, is basically using Google Sheets to build line graphs, which you've probably done before, but it's just always a good idea to make sure everybody knows how to do it. Okay, and also review the use of y equals mx plus b. Okay, which I know you guys have already gone over in math. Okay, but it's still something that's worth reviewing because it's something we use quite a bit in Science 10, okay? Especially for our lab that we're going to do on Tuesday. Okay, we're going to be using exactly the same stuff. We're going to be building graphs with Google Sheets, using y equals mx plus b to calculate stuff. So important stuff for us to go over. So what you have, okay, is this graphing lesson here, and there's a Google Sheet with your name on it. I want you to just open that sheet up, okay? And in there you'll see actually a few different sheets, okay, that have different things that we want to graph on them. Okay? So what we're going to do is just kind of run through how that graphing stuff works and then kind of go from there. All right? Now, before we get to that, sorry guys, I opened the wrong file here. Always when you're watching, right? If I turn away, it'll finish loading. See, I turned away. All right, so we just want to quickly go over some stuff to do with graphing here. And the first thing that we want to talk about is the purpose of graphing. Okay? The purpose of graphing is to show data that might otherwise just be a bunch of numbers in a table, okay? In a way that allows someone to see the general trend or the general message that your data is trying to convey. Right? So, for example, if I look at this graph, this is a pretty good graph. It tells me that what's on the graph is temperature and photosynthesis. Okay? I can see that on the graph, temperature was the manipulated variable because it's on the x-axis, and that photosynthesis was plotted as a function of that. So just looking at this graph, I know that this person ran an experiment where they measured the rate at which a plant carries out photosynthesis as a function of temperature. Okay? And I can see from their data that there was a definite trend towards photosynthesis got faster as temperature went up until we got to about 30 degrees, and then it just fell off. Okay? For whatever reason, photosynthesis just falls off after 30 degrees Celsius. Okay? So, does that tell me a fair amount about photosynthesis? It does. Okay? It tells me that plants are really good at carrying out photosynthesis unless they get too hot. Okay? Everyone all right with that? Now, how long would it have taken me to get that from a bunch of boxes with numbers in them? Quite a bit longer? Right? This is a graph gives someone a quick reference to what your experiment is saying, what your data is saying. Okay? That's the purpose of a graph, to represent otherwise maybe confusing data visually in a simple way. Okay? From a graph, we can also calculate a bunch of things, and we can extrapolate for stuff that is beyond the graph. Okay? So this graph only goes to 40 degrees Celsius. Okay? But I could probably use it to calculate maybe what would happen below 0 or after 40. Now, with this graph, maybe not so much because it just flattens out and just goes down to nothing. But okay, I might be able to extrapolate for below 0. It's probably also going to be around 0 because water doesn't typically evaporate very well when it's frozen. Okay. All right, is everyone okay with that idea? Okay, so let's go through how to build a graph with Google Sheets. So if I can get you guys to have open the first sheet that is about the relationship between diameter and circumference. Okay, so what I want to do here is I want to build a line graph of that data. Okay, to do that in Google Sheets, I want to highlight all of my data. Okay, so I just click and drag until all of my data turns that kind of faded blue color, okay, and it has a blue box drawn around it. Then I go to Insert, and I tell it I want to insert a chart. Okay, so I click on Chart. Right? And Google Sheets will then try to pick what type of graph it thinks is best. I'd say it's right about half the time. Okay? In this case, this is the kind of graph I wanted, an X, Y scatter plot. Okay? If you don't get a scatter chart, okay, you just go here to Chart Type on the right, click the down arrow, and it shows all the different chart types that you could possibly pick. Okay? Scatter is down here below pi and all of those other things. It already picked scatter, so we're good. Okay? Is everyone kind of at the same point as me? Okay. Now, I don't have a line on this graph yet. In fact, it's missing a few things. Okay? I mean, it does have my labels, which are important. A graph without labels is very misleading because I have no idea what's on that axis. So those are already on there because I put them up here. Okay? The titles, okay, it tells me what's on the graph, but you can always get a bit more creative with your title. Okay? I could call this the circle of life graph or something, I don't know. But yeah, we could call it something about circles. Okay? But I don't have a best fit line. Okay? So I need to get a best fit line on here. The way I do that is I go out of setup and into customize. Okay, so over here on the right, I click customize. And this is where you can do all kinds of things to the appearance of your graph. Okay, we've already done the chart style. Okay, we can change things in there, like the background color and the border color and all that. I very rarely do anything with that. Okay, chart axis and titles. This is where I can change things like the title, okay, or my axis labels or whatever. But they're already pretty good, so I probably don't need to do anything with that. Series is where we do the most work because this is dealing with our data points. Okay, so if I'm going to click the drop down there for series, it shows that I have circumference plotted as little blue dots. You can change that if you want. You can make them whatever shape you want. Okay, you can make them circles, or you can make them triangles or diamonds or stars or squares, whatever. Okay, I'm just going to leave them as circles. I usually make them a little bit smaller. I usually make them 2 pixels as opposed to 7, just because I find 7 like really big. Totally up to you though. Okay. But I scroll down because I want to put a best fit line on here, okay, or what Google calls a trend line. Okay, so there's a little checkbox further down that says trend line. And if you click that, or check it, it'll draw you a line of best fit. Okay. When you click trend line, more options show up underneath. Okay, those options will be the type of line. Okay, do you want a linear line? Do you want a polynomial line? Do you want an exponential line? We want a linear line. Okay? And it gives you the option for how thick you want the line to be. You can change that. You can change the line color. Okay? The biggest thing is the label. Okay? It's defaulted to none, but we want to get the equation for the line. Google will calculate y equals mx plus b for you. Okay? If you click use equation. All right, so once I do that, I get here that the equation for the line is y equals 3.1 times x plus 0.149. Okay, so this is y equals m, so m is 3.1 times x plus, and then 0.149 is b. Okay, so my y-intercept is b. Okay, and my slope is 3.1. In fact, my slope is 3.14. Yeah. Okay. It's what? Pi. Because pi is the relationship between diameter and circumference. Okay. If I divide the circumference by the diameter, I will always get pi. Okay. And that's why the slope of that line ends up being pi. Okay. So let's have a look at what that looks like here. This is totally different data. Oops. I grabbed the wrong data. There it is. Okay. So I get my data on there, okay, and my graph looks like this. In fact, the last time I did it, okay, I got 3.14, okay, and I got a y-intercept that was practically 0. Okay, is it good that my y-intercept is practically 0? It should be, because what's the circumference of a circle with no diameter? 0, right? It's a dot, okay? It's not a circle. Okay? So when I do this, okay, I get this line here. Now, here's my equation, okay? Y equals m times x plus b. If I want to manipulate that equation for slope, what do I do? What do I move first? B, yeah, so I subtract b from both sides, and then I divide by. I'm trying to get m by itself. What would I divide by? X. Okay, so we said the slope is pi, okay? And that makes sense because if I take any of the y values and divide them by x, I should get pi because y is circumference. X is diameter. Okay? If I divide those two, I should get pi. Okay? So it makes sense that my slope should be pi for that graph. Okay? Everybody all right with that idea? Okay, so the slope of your line, m, tells you the relationship, numerical relationship, between what's on your y-axis and what's on your x-axis. When we start looking at our graphs that we're going to do next week, okay, on position and time, okay, position's going to go on the y-axis, time is going to go on the x-axis, and the slope of the line will represent the velocity of the object, because I'd be dividing displacement by time when I calculate the slope. Right? So that's what we're going to be looking at as we go along here. Okay, so let's go to the next one, which was the rubber band graph. Can you guys go to the rubber band sheet? Okay, I'll give you guys a couple minutes. I want you to build a graph just like we did for the last one with this data. Okay, so highlight it all, insert chart, build it all. Okay, I'll give you a few minutes to get ahead of me and then we'll go through it together. Okay, so we highlight everything, we insert a chart. Okay, and again, it picked the right kind of chart here. We got stretching force as our manipulated variable. Okay, length of the band in meters is our responding variable, which basically means we put some sort of like spring scale on there, and we said we're going to pull it to 5 newtons, and then measure how long it is, pull it to 10 newtons, measure how long it is. Okay, that was the experiment that was being run. Right? So we want to go to customize because we've already got the graph built the right way. We just need to put on the line of best fit. So we just scroll down here in the customize the series part, check the box for trend line, and hit the label box, put in use equation, and we've got our graph built. Okay, so it really doesn't take long. That's the nice thing about Google Sheets. Okay, 10 years ago, if we were doing this, this lesson takes 3 days because everybody has to build these by hand on graph paper. Okay, well, yeah, it makes me want to puke too. Okay, this is so much better. Okay, all right, so now we've got that. Okay, now we can look at doing a few calculations with it. So I'm going to go back to this here. Okay, so what I want you guys to do is I want you to calculate a couple of things for me. Okay, actually, we're going to walk through this together. I'm just going to bring the graph over. Okay, I want to calculate how long the rubber band will be if I stretch it with 15 newtons of force. Okay, that's beyond the graph, so it's not a value I can read off of the graph. It's a value I have to calculate. Okay, what I know right now is that for this graph, y equals 2 times x plus 6.5. Okay, now they want me to calculate the length of the rubber band. So what part of that equation am I solving for? Y or x? Okay, so I'm looking for how long, which axis has length on it? The y-axis has length on it, yes? Okay, so that means that question is asking me to solve for a y value using what they gave me, 15 newtons worth of force. Well, I can see from the graph that force in newtons is on the x-axis. That means that is an x value. Right? So I'm going to substitute in 15 newtons for x. And I'm going to solve for how long the rubber band will be, okay, when I stretch it with 15 newtons worth of force. Everybody follow what I'm doing there? Okay, so I plug in my numbers here. So 2 times 15 plus 6.5. Okay, so we're going to have 36.5. And it'll be centimeters. Okay, so that's how long the rubber band will be if I stretch it with 15 newtons worth of force. Everyone all right with the math of that? Okay, now let's look at the understanding of the graph part of this. Okay. How long is the rubber band if I don't stretch it? So if I apply no force to the rubber band, how long is it? 6.5 centimeters. How do we figure that out? I see that number here in my equation. It's the y-intercept. Okay? Does the y-intercept tell me what the value of y is when x is 0? Okay, well that's how we figured it out then. How long is the rubber band when there's no force on it? Well, if there's no force, x is 0. Y is 6.5. Okay? What does the slope of this graph tell me? So it says the slope is 2. That means the graph goes up 2 centimeters for every 1 bit of x. So if I apply 1 more newton of force, how much longer will the rubber band get? 2 centimeters longer. Okay? The slope is 2 centimeters per newton because it's y divided by x. Okay? And that slope is saying that it'll get 2 centimeters longer for every newton of force that is applied. All right? So if I apply 2 newtons worth of force, it's going to get 4 centimeters longer. Okay? And so on and so on. Everyone okay with that idea? That's an important thing that we have to be able to do. When we look at a graph and we have the equation, we have to understand what the slope represents and what the y-intercept represents on a graph. Okay? The slope always represents the change in x, or sorry, the change in y as a function of x. 2 centimeters per newton. Okay? That tells me 2 centimeters longer for every extra newton of force I put in. Okay? All right. For number 2, they want to know how much force is needed to stretch the rubber band so that it's 18.7 centimeters in length. Okay, what are they asking me to find, y or x? X. They're asking me to find a force. Force is on the x-axis. Okay, and what did they give me? They gave me y. They gave me something in centimeters. That's how you can always tell. Look at the units. Okay, they're going to ask you, calculate this thing, and here's this thing. Okay, the thing they gave me, 18.7 centimeters. Centimeters is on the y-axis. That's a y value. Calculate x when y is this number. All right, so that means then I've got to take this formula, y equals 2 times x plus 6.5. And I've got to manipulate it to solve for x. So what should I move first? I'm supposed to move what's not attached first. What's attached to x? The 2. Okay, so what should I move first? The 6.5. Yeah. Okay. So I'm going to subtract. I got to do the opposite if I want to move it. So I'm going to go y minus 6.5 equals 2x. How do we get x by itself? Divide by 2. Okay, so now I should be able to solve for what x is when y is 18.7. All I have to do is plug in 18.7 for y. Okay, does this ringing a bell from math class? I hope it is, because you're supposed to do it in math. All right, so we take our 18.7 minus 6.5, and we divide it by 2. Okay, so that is telling me that it will be 6.1. I'll be using 6.1 newtons worth of force to stretch it that far. Okay, everybody all right with that? Okay, these are exactly the kinds of things I'm going to ask you to do in science. I'll give you a graph, or you're going to build a graph, like on Tuesday, build a graph with our data, and I'll ask you to calculate some things that are beyond your graph. So if we're looking at how far a car travels in 3 seconds and we graph that data, okay, I'm going to ask you how far would it travel if I could have let it run for 10 seconds or 20 seconds, okay? Or how long would it take for it to go 10 meters, okay? And you're just going to manipulate your graphing equation for y and x, okay? I'll give you the x, you solve for the y. I give you the y, you solve for the x, okay? All right, let's try one more here. Let's look at, what's our next one? Book thickness. We got time. We got time to do this one and the multiple run graph. Okay, build me a graph. Okay, this is a graph talking about how thick a book is based on the number of pages it has. Okay, so if we're building that graph real quick, okay, we insert our chart. Okay, it picks the right one. We go to customize. We get the series. We get our trend line and our label. Okay, and we're good to go. All right, so on this one here, we've got an equation that is 0.15 times x plus 5. Okay, so that's telling us then that the book is going to get 0.15 millimeters thicker for every page. Okay, so basically the slope is telling us the thickness of one page. Okay, it's 0.15 millimeters thick. Okay, all right, so if we're looking at what we can calculate with that graph, all right, so we've got 0.15 times x plus 5. I would like you guys to do those first two. We already did number 3. Okay, we identified that the slope told us the number of millimeters per sheet, or how thick one sheet was. I would like you guys to try questions 1 and 2. I'll give you about 5 minutes, and then we'll go over those. Okay, so let's look at this one. For question number 1, they want us to calculate the number of sheets in a book that is 80 millimeters thick. Are they asking us to calculate y or x? X. Number of sheets is on the x-axis. All right, so I'm looking to solve for x, so I'm going to manipulate, I'm going to subtract b, and then divide by m. So I will have y minus b over m equals x. Okay, did they tell me what y is? Yeah, 80 millimeters thick, right? Millimeters thickness, that's on the y-axis. So I know that y is 80. I know that b is 5 millimeters. Okay, and I know that m is 0.15. Okay, so if I go 80.
500.
What's that?
500.
Is that what it comes out to? 500 pages? Okay, so it comes out to 500 pages. Okay, everybody all right with that? Okay, and for number 2, they want to know the thickness of a book that has 805 pages. Okay, so they gave me this time x, the number of pages or sheets, okay, and they want me to find y. So that's a little easier because I don't have to manipulate, I just have to plug in my numbers on that one. So we'll have 5 times 8, sorry, not 5, 0.15 times 805 plus our 5. Okay, so 0.15 times 805 plus 5. Okay, so it would be 125.75 millimeters thick. That's a thick book. That's War and Peace. Okay, that's super thick. All right. Questions on that one? All right. What does B represent? It's the y-intercept. What does the y-intercept represent on this graph? Remember, the y-intercept is always telling us what the value of y is when x is 0. So this is the thickness of a book with no pages.
The covers?
It's the cover. The y-intercept on this graph would be the thickness of the book's cover, 5 millimeters. So it's probably a hardcover book. Okay, that sort of makes sense. These are the kinds of things that are that show I can interpret what's on a graph. Okay, like that's a bit of a tricky question, right? But we're thinking about, okay, this is thickness and pages and blah blah blah. But why do I have a thickness when I don't have any pages? Well, because books have covers. Okay. Things like that, little things. All right, last one we want to do here is the multiple run graph. Okay, so that is right after book thickness. Okay, so to do a graph with multiple runs, do exactly the same thing we've been doing. Highlight all of it. Okay, insert your chart, all of it will go the same. Except, what did it do? Did it pick the right kind of graph? Okay, what do I do now? Yeah, I gotta change it. So I gotta go over here to setup. Okay, and I've gotta click where it says column chart, and I've gotta scroll down to what kind? Scatter. Scroll down here, okay, click on scatter. That's better, okay? That's 3 sets of data, okay? Yellow points, red points, and blue points, okay? And I didn't get a label on my y-axis this time, so I'm gonna have to put that in for myself, right? That goes in under customize, right? Chart axis and titles, and I want to change it from chart title to vertical axis title. Okay, right now there's nothing in there, so I'll type in position in meters. Okay, so as soon as I do that, it shows up there. Now I've got a properly formatted and labeled graph. Now I can do all the stuff we usually do. Okay, I go to series, and I'm going to change my circle size to 2 pixels, and I'm going to go to trend line and use equation. All right, so when I do that, I get an equation for each of the lines. That's important, they all have different slopes. Okay. All right. Is that title any good? I don't really like that title much myself. You can edit it right in here directly. Okay. Grab. No, grow up. Okay, so now that I've got that, now I can go and calculate what I need to calculate from there. So, okay, I would like you guys to tell me what the velocity of each cart is, the position of each cart after 12 seconds, okay, and how long it will take each cart to reach a position of 50 meters. Spoiler alert, I'm going to ask you the same 3 things in the analysis questions of your lab on Tuesday. So if you pay really close attention, you'll know exactly how to do your analysis on Tuesday. Okay, I'll give you a couple minutes. I'd say for sure you guys can do 2 and 3. 1 might be a bit of a weird one for you for right now. So maybe try 2 and 3 first, okay, and then come back to number 1 after that. ironically, number 1 requires no calculating. 2 and 3 actually do. Okay. Okay, let's have a look at 2 and 3 first here. Okay, so if I want to calculate the position of each card after 12 seconds, what part of y equals mx plus b am I solving for? If I'm looking for position, which axis is position? It's on the y, right? Okay, so I'm looking, whenever I'm asking myself that question, that's what I got to look at. I got to look at my graph and go, okay, they want position, position is on the y, I'm solving for y. Okay, so then I just plug in my numbers, right? So for my blue car, okay, so for the blue car, I've got y equals 1.38. Okay, they told me that the x value is 12 seconds, so times 12 plus 9.52 times 10 to the minus 3, that's 0.00952. Okay, all right. So 1.38 times 12 seconds, okay, plus, it was plus, right? Yeah, 0.00952. All right, so for the blue car, that'll be 16.6 meters. Okay, for cart number 2, which is red, okay, it's going to be that y will equal 2.01 times 12 plus negative 0.0524. Okay, so we're looking at 24.1 meters. And that makes sense because y is faster than, or sorry, red is faster than blue. Okay, the line is steeper, okay, so it's faster than the blue car, so it should go further in 12 seconds than the blue car did. Okay? And then the last one, okay, is for the yellow car. Okay, so that will be y equals 3.39 times 12 plus 0.0381. All right, and that being the fastest car also makes sense that that would be 40.7 meters. Okay, everybody all right with that? For number 3, how long will it take each cart to reach a position of 50 meters? Okay, how long means they want me to calculate what? Time. Which axis is time on? X. Okay, so looking for the x-axis here, or looking for the x value. So I have to manipulate for y equals, or manipulate y equals mx plus b now for x. Okay, so y equals m times x plus b. Okay, so I subtract b from both sides, divide by m, and I've got x by itself. So for the blue car, that's going to be 50 meters. That's the y value they gave me, minus 0.00952. That's b. Okay, divided by m, which is 1.38. Okay, so for the blue car, it's going to take okay, 36.2 seconds. Okay, now something you have to watch out for with this particular manipulation is order of operations. Okay, notice when I did this, I did the subtraction operation and hit equals, and then divided by the slope. If you put it all in one line, it does the division first, and then it subtracts whatever you divided from 50, and you do not get the same number. Okay, so just be mindful of that. You have to do the top, then do the bottom. Okay, don't try and do them all in one operation on your calculator. Okay, for the red carts, okay, so for the red one, we're looking for how long that will take. Okay, it will be 50 minus 0.0524, okay, divided by 2.01. so we're looking at that'll take 24.9 seconds. And for the yellow car, it'll be 50 minus 0.0381, okay, divided by 3.39. And we get the smallest amount of time because obviously that's the fastest car, 14.7 seconds. All right, last thing, question number 1. Normally, or we learned the other day, that you calculate velocity by going displacement divided by time. Okay? Now, we haven't done any of this, but I did mention this the other day. Your displacement is your change in position. It's how much you change your position by. It's a vector quantity. It contains direction as well. So, when we calculate the slope of one of these lines, okay, what we're doing is we are taking y minus b. This is a position, and this is a position, and we're dividing it by x. Well, what's on the x-axis? Time. So I'm taking here y, which is my final position. I'm subtracting b, which is my position at time 0, or my initial position, and I'm dividing it by time. Essentially, I'm going displacement over time. So when I calculate the slope of a line on this type of graph, I'm figuring out the velocity at which they travel in meters per second. Okay? Because when I do the slope, I'm dividing meters on the top by seconds on the bottom. I get units of meters per second. Those are the measure of velocity. Okay? That's what we're going to be focusing on more on Monday, and that's what our lab will be on Tuesday. Okay? Today was basically just about reviewing y equals mx plus b and how to build the graphs. Make sure you're signed out, powered down before you close the lid. Put them back in the right slots, please.